All right, so we can start. So we've been discussing various topics, but last lecture we were looking at delay in bipolar transistors, and so here is a simple 1D schematic of the bipolar transistor. We have, as you can all identify, we have emitter, we have base, and we have collector. Emitter is N plus. We are talking about NPN transistor. This is P, and this is N. All right, and we are looking at delay in here. There is, of course, a depletion region between emitter and base. It's mostly, if you look at it here, it's mostly on the base side. And there's a depletion region associated with the collector base junction here also. So these are depletion regions. These are depletion region. This is also a depletion region here. Right, so depletion regions are here. And we've been saying that delay, you can estimate delay by looking at how much charge you have to supply and the amount of current that is available for supplying that charge. So we've been looking at one delay, which is delta Q by delta JC here. And delta Q is made up of, as you can see here, there are 5 components which are shown here. This is the junction depletion charge here. This is the junction charge associated with the collector base junction. These are the electrons stored in the base, electrons which are injected from the emitter. We are talking about forward bias. These are electrons stored in the collector because the electrons move across the depletion region, and each one of these components results in delay. So we have seen this results in a delay which is given by here. The capacitances are per unit area. This results in CJC, KT by Q, JC. Collector area, we said this one-dimensional picture is limited. Collector area is different from emitter area, so we add this particular factor. We add this factor here. This is equal to, this results in base transit time, WB square effective base width. So this is the effective base width, the neutral region, right? So this is the effective base width. The actual base width, which is called the metallurgical base width, is bigger. This one is because of holes stored in the emitter, the holes which are injected from base into the emitter. So this is WE square emitter. This is the emitter thickness. WE here, WE squared by 2 dP divided by beta here. And one last component, which is the electrons stored in the collector. So that's, we will show today, is equal to WC by 2V sat here. This is the WC here, right? The thickness of the collector depletion region. And that's equal to, and this is equal to the saturation velocity. Right, so these are the 5 components of charges, each one resulting in a particular delay value here. All right, so you can see that they belong to 2 different categories. One category is these delay. And this depends on, if you can see here, collector current density. If you change collector current density, if you operate the transistor at higher collector current density, you will get lesser delay here. And then the other category is this one here. These are all, they're independent of, first order, they're independent of collector current density. These are all called, they go by the name. These are different transit times. We just call them transit times. Right, so two blocks of delay that you see. One component dependent on current density, the other component first order independent of current density. All right, so what we want to do is we had discussed a little bit the source of this particular delay, the collector transit time. And I also mentioned that if you really try to create a transistor with very high speed, then you will eventually get limited by this particular transit time, eventually. So let me also add here that this is related to Ft is 1 by 2 pi tau. Okay, all right, so that's sort of summary of what we have done. Let's look at the collector transit time here. Okay, so what we are talking about, you're assuming that this is a WC, right? And so we are assuming that electrons are starting from here, they go here, come here, and then they go through this, and eventually the electron comes here. And if the current density is Jc, then we've already said the number of electrons here is going to be Jc is equal to Q Vsat times Nc. It's basically drift current, and we assume that all the electrons are moving with saturation velocity. So that's obviously an approximation. As they enter the depletion region, their velocity will not be saturation, and then they will gradually pick up. As the field increases, it will eventually reach saturation velocity. So it's an analytical model. We make approximations, and so from here, what we get is Nc equal to Jc by QV set. Okay, so now imagine, so what we are looking at is this collector depletion rates. So imagine initially Jc equal to 0. Initially Jc equal to 0, which means I have not, so you could imagine, let's say this is ground. You're reverse biasing the collector, so you're applying a positive voltage here, right? And let's say you've also applied 0 here for a moment. So you're not injecting anything, right? And then you can apply an emitter voltage, so you start to inject, right? So by altering this voltage here, you can change the collector voltage, right? VE. So Jc initially, let's say, is 0, and then therefore the total charge in the depletion region, Q. See whether the charge in the depletion region, I can write QC is square root 2 ES Q in DC multiplied by VBI plus, in this scenario, VC. This is VC. Now, of course, I've made an assumption that the collector doping in the C is much less than Na, the base doping. For example, the collector doping could be, let's say, 5 times 16. We'll show you an example, and base doping is, let's say, 2 times 17. Or this could be even lower. So it's an assumption one can write more accurately, taking into account the base doping and all that. So let me put here this thing here, approximate sign here. So this is the charge in the depletion region. Charge in the depletion region is what? Basically equal to Q NDC multiplied by WC, and then you write down expression for WC, so you end up with getting this one here. Okay, so that's not an issue, right? Okay, now I apply a JC in the sense that I increase VE and a collector current starts flowing. So the charge now QC dash becomes square root 2 ES Q. Now this become NDC minus JC by QV sat VBI plus VC. this is what happens here. The charge becomes this much because in addition to the doping, in addition to the charge due to the doping here NDC, there is a charge also. Note that this is positively charged NDC. Now there is this thing coming in here. NC equal to JC by QV sat. So it subtracts from here. Right. So as a result of this change in JC, there is a change in charge here, delta Q. Right. So we want to calculate what is the change in charge. And so the collector, this delay associated with this is, we will call tau C as delta Q, this delta QC that you would like, by JC minus 0 here. So initially, this JC and then it is 0, so JC minus 0 here. So we would like to call this as a delay associated with electrons moving across the depletion region, and therefore we call this as a collector transit time. Is associated with electrons making a transition or going through the collector depletion region. And as they go through the collector depletion region, there's a certain amount of charge. So that's all our estimates of delay are derived by looking at how much charge do I have to add and what is the current available for this thing here, right? So let's calculate that. So delta QC is square root 2 ES Q NDC, what have I written? VBI plus VC minus square root 2 ES Q NDC minus GC by QV sat VBI plus VC, right? So this is what we are calculating. So we're looking at small increments, so we can take this out, 2 ES QNDC VBI plus VC, 1 minus, we'll get square root NDC minus JC by QV sat by NDC. Is that okay? That's fine. Okay. So if I look at this particular term, I will get 1 minus JC by QV sat NDC half, just this term here, and then we'll approximate it 1 minus half JC by QV sat NDC. We'll do that, approximate it here. So then our estimate of delta QC comes square root 2 ES QNDC VBI plus VC multiplied by 1 minus and cancels, multiplied by half JC by QV sat NDC. All right, so now what we need to do is delta QC by JC. And it's a small step here. This will be WC by 2 V sat. WC is what? The depletion region. So depletion region is WC is square root 2ES by QNDC VBI plus VC, depletion width. Right? It just comes out how much, as you know, for current JC to flow through the collector depletion region, I have to add amount of charge, extra amount of charge. Right? And the extra charge divided by the current gives me the delay. And the delay comes out to be this one here. Note that it's interesting that all the mobile charges that you will take, and when you divide it by current, they all come out to be a constant term. It's independent of current density. These are all mobile charges give rise to a delay which is a constant. And all fixed charges, depletion charges, give rise to a delay which is inversely proportional to the current density. Right? So a simple derivation of how much, the charge which is there in the depletion region, collector depletion region, and the delay that it will result in. All right, so let's then continue. So this then becomes the model of the delay in a BJT. And as I said, Ft equal to 1 over 2 pi tau, unity gain frequency. A complete model. All right, so let me show you some calculations. Let's do some calculations and see what the values of different components of delay are. What is the value of Ft? Let's look at a concrete example. Right, so now let's look at this particular picture here. So this is the two-dimensional view of the transistor. Note at the top here is the emitter. This is the region here, which is N plus region here. Then underneath is the base region here. All this is the base. The blue is the base region, and all this purple is the collector region here. And then, as we said, in order to make contacts and all that, you need a N plus region also. All right, so that's our transistor. In this case, I've just made a contact at the bottom for convenience, and I've given you a sample set of why these numbers make sense and all that will become a little bit clear later on. So we have taken note that base doping as 2 times 17. Base width is 0.3 micron from here to here. 0.3 micron is the base width. WB equal to 0.3 micron. Base doping is 2 times 17. Collector doping we have taken as 5 times 16. Collector thickness you can see from here to here, 0.5 micron. All right. Emitter doping 10 per 19. Emitter thickness 0.1 micron. Right? I mean, these are reasonable numbers for an initial transistor. Okay. All right. So the base is here. The base is formed here. Note that what is missing in this particular picture is, to form a contact, I need a P plus region here also. You will not, we have discussed this, you will not form a good contact unless you have a P plus region. So maybe more accurate is is this particular picture here, where under the base I put some 10 power 18 also, right under the base. But here is 2 times 17. There outside the base, so this is the transistor, actual transistor is running here between, between these points here. This is the transistor running here, okay. Outside this is what we have used for making the P plus here. So this is a more accurate picture, but all that it does is it alters the contact resistance and all that. Otherwise it doesn't change too much here, okay. All right, so any questions regarding the structure? So I'm going to use, do some calculations and also use Silvaco, which is a tool for a device simulator, which solves Poisson's equation, continuity equation and all that, and gives you current, voltage, capacitances, everything, right? So we'll use that for more accurate results and our own simple analytical calculations to get an estimate, to understand, okay? So this is the picture of electric field at equilibrium. Does it make sense? Electric field at equilibrium. 0 is starting here at the top, and then as you go to 1 micron, you go and is the other end here, 1 micron here. So does it make sense what you see? If I maybe what I should do is I should blow it up so that you can see properly. Electric field. So where are we going? Note that we are going from here, from the top, and we are going down. Okay, and so we are starting from the top and going down. So this large electric field is where? This is at equilibrium. No voltage is applied anywhere. Emitter is 0, base is 0, collector is 0. So what is the first large increase in electric field? This depletion region. And then there is the other depletion region, which is here, which is negative, okay, because this is a NP junction, and so the field is in NP junction, the field is from positive to negative, so it's fine, and this is here. So this is the other junction here, right? And note that little bit of space charge region, I won't call it a depletion region. See, a more general name for these things are not depletion region. Wherever you see charges because of movement of electrons and all that, it's a space charge region. So this is a space charge region, 1 here. There's another space charge region here, and then there is a little bit of here also. Why? Because here is the doping is here is 5 times 16. 5 times 16, and the doping here is some 10 per 19. So whenever you have a difference in doping, you see something happening there. All right, so let me show you here a bigger picture of this. So all of you expect electric field in a junction goes linearly, right? So that's what you see, linearly. These are simulation results, so these are sort of exact. So one important point to note here is the following. This is at equilibrium. So if you look at the extent of the depletion, so my base starts from here. Base starts from here and ends here, right? So 0.1 to 0.4, and so the base width that I've designed is 0.3, right? But what happens is, note that the depletion region is almost reaching till here. And from the other side, the depletion region is reaching till here. So the actual base width is significantly smaller. It's significantly smaller here. So only this much. At equilibrium. Only the neutral base width. Now what would happen is, as you forward bias the base junction, this point will move here. This point will move left because the depletion width will shrink. And this point, as you apply reverse bias the collector base junction, this will also move here. So, you know, when you take a bipolar transistor like this, let's say here, consider the following situation: ground, ground, and ground. Right? This is the situation that I'm showing you. And this situation is what is the device is obviously supposed to be off, correct? Equilibrium, no current is flowing, this is fine. But now in many devices, for example, if you're making an inverter or amplifier and all that, it can happen that this node that, let's say an inverter, simple inverter. So when you apply 0 and you apply, let's say 5 volt or 2 volt or whatever, the voltage here will turn out to be 5. Because you have not applied anything to the base, emitter is ground, so base emitter, the transistor is still off, but the voltage at the collector is 5 volt. Right? So in this sense, what I'm saying is, from the point of view of the base width, this is the worst case situation. Because what would happen is you have not applied anything here. So this junction is, this width is maximum. Because base emitter junction is normally forward bias or zero bias. While when you apply 5 volt here, this is equilibrium. At 5 volt here, this will further move here. Will further move left. Now what may happen is, under this situation, if the two depletion regions touch, right, then we say this is punch through. These things happen in MOSFETs also. If you're not careful, here we are talking about depletion region due to collector and emitter touching each other. There we talk about drain and source maybe touching each other, influencing each other, or they come too close to each other. Right? So that's the problem. So what you have to do is, a bipolar transistor, we will just show, will not work properly unless you have a well-defined neutral region, neutral base width, under worst case scenario. Under the worst case operating point, which is the worst case operating point is when collector is at the highest bias and base emitter junction is not forward bias. Then what happens is, base width, WB effective, is minimum. And under such condition, we don't want punch through to occur. Otherwise, your transistor is supposed to be off, but it will start conducting. Okay, it will start conducting. Why will it start conducting? We'll see in a minute. All right, so that's where you have to choose carefully the total base width. Suppose I had chosen here not 0.3 but 0.2. It's quite possible that if I apply 5 volt, punch through would occur, and your transistor will not work properly here. So you have to choose the base width. You cannot arbitrarily make the base width small here. So why am I saying let me point to this punch through part here. Just show you a little bit on punch through before we, what is the importance of punch through here. So let's look at, we are talking about two depletion regions. Two junctions here and here. So there's a depletion region associated here, and there's a depletion region associated like this here. Two depletion regions. So if you look at the band diagram, N and P, this is N, this is P, and this is N. If you look at this band diagram here, so you've all seen this band diagram when you draw conduction band and valence band and all that. So let me just sketch. So what would happen is, let's say conduction band, valence band will also go like this here. So it will go like this, EC I'm drawing, then it comes here. Then conduction band, and this is the edge of the depletion region, right? So conduction band will go, I'm not drawing exactly, it goes like this. And then becomes constant till here. And then conduction band will go. Let's say, this is at equilibrium, so I can draw a Fermi energy, let's say almost like here. So conduction band will go. Like this here. Or if I've applied a reverse bias, let's say if I've applied a reverse bias, it will go like this here. All of you might have seen diagrams like this. If I've applied a reverse bias, collector depletion region, a voltage equal to, let's say up here, say I apply 2 volt. So let's say this is 2 volt. Base emitter junction is this thing here. Now the issue is, why does the current not flow? Because there is a big barrier here, built-in voltage here. This built-in voltage is the order of, we'll show you some calculation, maybe 0.9 volt. Right, so an electron cannot cross this particular barrier and then go and all that. It cannot happen. Okay, so no current flows in this case. But suppose I apply, instead of 2 volt here, suppose I apply 5 volt here. Right, if I apply 5 volt here, the depletion region will, suppose what happens is it comes till here. The two touched each other. Let's say this is 5 volt. Or let's call this is the punch through voltage, VPT. I apply a voltage large enough so that there is no depletion region, neutral base width, nothing is left. The two depletion regions touch. Right, so why is punch through such a phenomena that you want to avoid? The two depletion regions have touched. So the band diagram looks like this, the red one now. Right, now keep in mind, why are the electrons not able to flow? What is the reason? There is this barrier, correct? Now you apply a voltage larger than punch through. What do you think will happen? A voltage larger than punch through. The depletion region is already gone. So when you are applying a voltage more voltage in the collector, what does collector want? The more voltage has to be dropped, right? It has to be dropped somewhere. You apply 5 volt, it needs some place for the voltage to be dropped. Voltage to be dropped means what? It needs electric field. Electric field means what? It needs charge. So now you've applied a voltage more than VPT. It needs charge for that extra voltage. Where will that charge come from? So note that the two have already touched. So this is the situation, right? Here, what is happening is, this is the one edge, this is the other edge, and this is, let's say, whatever. The two, there is no, from one side is one depletion region, from the other side, the other depletion region. The two depletion regions are already touched. So now what will happen? You've applied more collector voltage. So the collector, it needs, so what it will do is it will try to eat into the other one. It will try to take the charge from the other one. So the net effect, we can actually, at some point, what we can do is how to solve a problem like this through Poisson's equation and all that. So what would begin to happen is that when that happens, when it takes away charge from here, then it has less charge left. And the other one gets more charge. So what happens is it begins to look like this. Less charge on this side, which means less voltage drop. And then it begins to go like this here. What has happened? Do you see something that has happened? Earlier, the barrier height from here to here has become less, which means what in effect is as if the junction is getting forward bias. How do you reduce the barrier? So now the electrons have an easier time going in here. You apply even more, it will become like this here. And the electrons have an easy time going here. So what happens is the transistor is supposed to be off, but the moment punch through occurs, a lot of current can begin to flow. A little bit more voltage, the barrier gets reduced, and the current begins to increase. So if I were to draw what would happen is, let's say collector IC versus VC, and VBE is 0, right? Almost negligible current. But then the moment you start reaching punch through, it starts to begin to increase. Transistor is supposed to be off, but it's starting to conduct, which means it's no longer, the switch is no longer in the non-conducting state. So many times in the transistor, what may happen is, there are two things that can happen here. It's a reverse bias junction. Either the junction may break down or punch through. Both of these things will make the transistor conduct in the reverse bias case, which is not the required thing, which is something that you need to avoid. So both these phenomena you have to, when you're designing a transistor, you have to make sure that breakdown doesn't occur at, whatever is your maximum collector voltage, VC, whatever voltage you want to operate at, you have to make sure that breakdown doesn't occur and punch through doesn't occur. Both of these things you have to avoid. So this is one consideration when you're doing the design. By choosing the base width and other things, you have to avoid both of them. Breakdown and punch through. And then you design and you optimize your base width and things like that. But you have to make sure that these things don't occur. Breakdown and so both of these things you should be able to calculate. Breakdown and punch through voltage. Given a junction, you should be able to calculate both of them, because that's absolutely essential for designing a bipolar or a diode or any of these semiconductor devices. You need to be able to compute both these values here, breakdown and punch through voltage. So punch through only requires that you compute both the depletion regions from this side and make sure the voltage at which the two depletion regions touch, that is the punch through voltage. So this is, if you know how to, so the basics of calculating punch through is your ability to calculate depletion width. If you know how to calculate depletion width, you'll be able to calculate punch through voltage. And breakdown voltage also, the ability to calculate breakdown voltage is nothing but, we said, breakdown occurs when the electric field, E maximum, reaches a critical field, E critical. E critical is about, let's say, 3 times 10 power 5 volt per centimeter. So your ability to calculate breakdown voltage depends on your ability to calculate maximum field in the junction, which is again related to depletion widths and all that, right? So your ability to calculate, solve Poisson's equation in a depletion region and all that, and do these calculations is very, very important, very fundamental to all semiconductor devices. Calculating depletion widths, calculating maximum electric field, calculating capacitance, all these things are very, very basic things that all of you should know how to do that. All right, so that's, I'm pointing out in the design of the bipolar transistor why these are important. Okay, let's come to now some sample calculations. Okay, so I've taken this transistor. There are other interesting things that are there. So I'm taking this transistor with these characteristics, WB, 5, all these things that are there. And I'm going to show some analytical results and simulation results. So for example, this is a simulation result. All right. So if I simulate it, this is what I get. Collector current and base current as a function of base emitter voltage, where collector voltage is fixed at 2 volts, which means this plot is for forward active mode. This plot, when you plot IC and IB as a function of VBE with VC equal to 2 volts, it goes by the name called Gummel plot, by the name of one person who made a lot of contributions to bipolar transistor. Anyway. Right, so what you see is, note that this is on the log scale and this is on the linear scale. And note that almost like this is almost like a perfect straight line. And if I were to measure the ideality factor, I would get ideality factor equal to 1. So it just keeps on going, but then note that some interesting things are happening here. So this is IC So beyond a certain point, what is happening is somewhere around here is we are getting sort of saturation that you see, and here is where what is happening is high level injection is occurring somewhere, high level injection effects, because when you apply a lot of forward bias, VBE, lot of forward bias, lot of carriers are injected, and you start getting, it's no longer ideality factor equal to 1. There are things that are occurring inside. So this phenomena is also very important to understand and note here that you cannot arbitrarily keep on increasing IC by applying more and more base emitter voltage. Right? At some point you start seeing what is the consequence of this, because all of you know the ratio is important. Beta as a ratio is important. So let me show you the ratio. What happens as a result of this high level injection? Look at beta. This is a typical beta. These are a simulation, but similar things happen in experimentally measured transistors also. Look at beta here. Beta versus JC, current density. Beta is small, rises, reaches a maximum value, a small decrease here, and then sharp decrease. So this is where I would say somewhere around this, maybe let's say beyond this is becoming very, very high. So there's an upper current density, maybe somewhere here or so. Beyond that, if you go, the beta is falling very, very sharply, may become negligible or may become very small. So there's an upper limit. This is important because there's an upper limit of current density. You can't go beyond a certain current density. This is what this plot is showing. If you go beyond this, the beta is becoming very small. Even otherwise, beta is not very large, as you can see here. So if you want to know now, why is this beta going like this here? What is the reason for it? Why is beta rising? Why does it gradually fall? And why does it sharply fall? 3 different things that are there. Gradually increase, this goes, increasing, gradual fall, and a sharp fall. 3 segments, that if you would like, 3 segments in beta that you can see here. Segment number 1, segment number 2, and then segment number 3. Right? Segment number 1 is primarily because of the base current that we have said is made up of the following. We said base current is, if I go back here, let's say here, we've said base current normally is because of holes which are going here. Right? But then there is a base current that comes about because of, we've also said, recombination within the depletion region. We have discussed that in a diode, that at low bias, there is recombination within the depletion region. And at high bias, then those things. And recombination within the depletion region goes as e to the power qv by 2 kt. Right, so note that base current is coming about because of these 2 factors. Recombination within the depletion region, which is e to the power qv by 2 kt. Injection into the neutral region, this goes as e to the power qv by kt. Right? So there are 2 components to the base current. If I were to write IB is maybe 1 component, I1, e to the power qv by I1 I can't write current, so K1, qv by kt, and K2, e to the power qv by 2 kt. These are the 2 components. Collector current is all the time is like this. IC is some IS e to the power qv by 1 kt. Right, so now look at the ratio, IC by IB. If this term is dominant, what do you think will happen to IC by IB? IC by IB becomes K2, K2, no, not K2, IS by K2 e to the power QV by KT into 2, correct? It goes like that. If this term is dominant. If this is there, can I write that this is like proportional to, this beta is proportional to square root IC? Right? So you are seeing now beta is what? Beta would increase with collector current. Beta would rise with collector current. Because IC is increasing as QV by KT. Base current is going as QV by 2 KT. Base current is not going as fast as IC. Therefore, the ratio increases. But eventually what will happen is, note that this term is increasing as QV by 2 KT. This term is increasing QV by KT. So what happens is this term becomes dominant. If this term becomes dominant, that what would happen is beta is constant. So what you would expect is, based on this, you would expect beta with IC should go like this. This should be like this here and then become constant. Right? You would expect a constant here. So at least you're getting an explanation for one segment, the initial rising segment. Why is it rising? Why is current rising? Why is gain rising with current density? Mainly because of when you see that phenomena, current gain is rising with current density, you know what is happening is there is depletion region. Base current is coming because of depletion region. Now, why is so this part is okay? The reason for it, let's go back to the other one. Why is the current falling here? What is the reason for this? It just falls here. So according to a simple theory, what should have happened is it should have remained constant. After a point, it should have remained constant, but it's falling. Okay. So what is the reason for this fall? First order. So what is happening is, if you look at here, n plus, so, going into the details of this is because it will help you understand the kind of things that occur in devices. So when you're looking at n plus p and n, note that what is happening is that there's a depletion region here and there's a depletion region here. And this is the effective base width. And so collector current, JC, is a short base diode, Q dN by WB effective multiplied by whatever carrier density, Ni square over Na and all that, e to the power Q VB by KT. It goes like that. So important point is WB effective. This is the WB effective. Now, how are you increasing the collector current? You're increasing the collector current by JC increase. So the way you are increasing the collector current is you increase the base emitter voltage and then causes the collector current to increase. So as the base emitter voltage increases, note that what happens to the depletion width? It shrinks. And as the depletion width small amount of shrinks, what happens is the effective base width becomes larger. And effective base width becomes larger, which means JC becomes a little smaller here. So this effect is because of that. Base width is becoming a little longer because the collector base junction, emitter base junction is getting more and more forward bias. So the base width is, emitter base depletion region is a little bit shrinking. So that region is effective base width increasing. So it's a small amount of falling here. And then this is an interesting phenomena that we will come later on. Then as you go to higher current density, what is happening is the number of electrons injected into the base are becoming comparable to the doping, the background doping. And this is what we call as the high level injection. So now what happens is JC begins to go as approximately, I'm saying, begins to go as QV by 2 kT. When high level injection occurs, JC starts going e to the power QV by kT, and JB is e to the power QV by kT. And therefore, if you take the ratio, you find that beta goes down. Now, why are we bothering about these high level injection and things like that? Do we really need to get into it? Well, let's do some calculations and see the numbers. Okay, so now this may be a little puzzling to you. We'll come to that. Why, when you go to high level injection, the injected current, wherever high level injection occurs. So the point that is being made is the following. Let me make the point clear. What is being said is, so if you take, let's take a junction like this. Suppose this is N plus and this P, just a diode, and there's a contact here. When there is low level injection, which all of you are familiar with, low level injection, current goes as J equal to Js e to the power V by Vt minus 1. But high level injection, J begins to go as some Js dash e to the power V by 2 Vt. Here. And if you want very simple reason for why this occurs without going into the too much details, one of the key things about a PN junction is the following. At the edge of the depletion region, we have been saying at the edge of the depletion region, the product of N and P is equal to Ni square e to the power V by Vt. We can show that this is more or less true under low level injection, high level injection and all that. The product of N and P is Ni square e to the power V by Vt. From this you can understand. In low level injection, what is the value of P here in this region? P is what? I mean, it's a P region, so the value of P is Na, right? In low level injection, the value of hole density is nothing but Na. So you write N then becomes Ni square over Na, what you're familiar with. But if it's very high level injection, so P that is injected is much larger than, let's say, the background doping. Then P and N become comparable because P and N are, delta P is always equal to delta N. Delta P is always, because it's neutral, delta P is always equal to delta N. Now, what we are saying is this delta P is much larger than Na. So then P and N are practically same. If P and N are practically same, each one of them is equal to Ni square over e to the power V by 2 Vt. Right? If N and P are exactly the same, then you will get N square or P square equal to Ni square e to the power V by Vt, and you'll get N is e to the power V by 2 Vt. So what happens is, low level injection, the injected carrier density is increasing as e to the power V by Vt. But the moment you start entering into high level injection is going to us e to the power V by 2 Vt. That's one of the main consequences of high level injection. It doesn't increase e to the power V by Vt. It increases as e to the power V by 2 Vt here. So that's the reason why I'm saying, now if you look at this is the reason why we are saying is collector current starts going as 2 kT. Now if you're wondering why is base current still going as QV by kT. So base current now, if you go back and see, where is the base current coming from? Base current is now coming from injection into here, into the emitter. And emitter doping is very high. So high level injection never occurs in the emitter because emitter doping is so high. It will never occur in the emitter. High level injection will occur in the base because base doping is low. So when high level injection occurs in the base, then collector current starts to become 2 kT, but base current still remains kT. So it's all a question of now each component is a kT or a 2 kT, and you have to look at when that occurs. Okay, so interestingly, base current starts off as 2 kT current and then becomes 1 kT current. Base current becomes 1 kT. Collector current starts off as kT and then becomes 2 kT. Right, so this kT and then 2 kT. And so this sort of explains why this is occurring here. What is this? Why this phenomena like this is occurring? Why this is rising in this way? This is one, and why this is falling here. It all has to do with how is the base current changing with the bias and how is the collector current changing with bias. Okay. So let me show you some results for the delay. Okay, so this is our device. Just keep in mind that I know all the dopings. I know doping, base doping, I know collector doping, all the dopings are given, all the thicknesses are given. So the first thing is we calculate the built-in voltage. So I calculate built-in voltage VBI as 1 volt for base emitter junction, and VBI for the other junction, for this junction, I calculate 0.837. Let's not get into it, what these values are. Then what I calculate is the depletion. So I'm assuming 0.7 volt forward bias is there. So I'm calculating the depletion width associated with this junction, which is XDE. And XDE comes out to be 45 nanometer. The formulas are familiar. I can share it later on with you, all the formulas, so that you can do we'll ask you to do a sample calculation. And then we can calculate the collector junction capacitance, which comes out to be so much. 2.28 into 10 power minus 7. These are per unit area, farad per centimeter square. And similarly, now we calculate the collector depletion width. Collector depletion width we calculate, it comes out to be larger because it's reverse bias, dopings are less, 300 nanometer. Note that this is very small, 45 nanometer, this is 300 nanometer. We calculate the collector junction capacitance, ES by XDC comes out to be 3 times 10 power minus 8. Note that collector capacitance per unit area is almost like 1 order less than the capacitance in the emitter base junction. I also calculate the effective base width, WB effective, this region here. That turns out to be 194. Note that the actual base width that I had taken, WB0, is 300 nanometer, 0.3 micron or 300 nanometer. Effective base width is coming out to be 194, almost like 200 nanometer. 100 nanometer has gone into the depletion regions. So this comes out here, right? So these are the basic calculations, all the depletion widths, all the built-in voltages, all the depletion widths, all the capacitances, you do the calculation, and base width, right? And now we are going to put in here all the terms, right? All the terms that are here and into this and calculate all the delays. Because now we have all the values, CJE we have, CJC we have, area of the collector divided by emitter, we have taken a ratio of 2 in our design. So this AC by AE is 2 here. And we have everything else before us. VSAT is 10 to the power 7. We've just taken centimeter per second, saturation velocity. All right, so if we do that, then these are the values. So at 0.7 volt, the current density in my device is 144 ampere per centimeter square. So the first delay that I calculate is because of the emitter junction capacitance. This delay comes out to be 41 picosecond. Everything is in picosecond. Next, I calculate delay due to collector junction depletion region. That comes out to be 12.34 picosecond. Next, I calculate base transit time. comes out to be 13.4 picosecond. Next, I calculate emitter because of holes injected into the emitter. We have said that that's going to be small because of the beta, that is 1.1 picosecond. Next, I calculate collector transit time, what we discussed today, a charge stored in the collector. That gives rise to 1.5 picosecond. I add up all of them, it comes out to be 69 picosecond. And then I calculate FT, 1 over 2 pi, FT comes out by 2.2 gigahertz. That my unity gain frequency of the transistor is 2.2 gigahertz for this design. Okay, all the components of the delay, you add up. Of course, it's a simple calculation that we are doing. Our calculations are not very accurate, okay? But we get a reasonable estimate here. Note that if I look at the analysis, the dominant delays in my device, if I'm just looking at the first two components, T1 plus T2 divided by total delay, comes to be 77%. Most of the delay is coming from where? Charging, discharging of the emitter base capacitance and collector base capacitance. Most of the delay is coming from there. When I'm forward biasing at 0.7, 0.7 is your favorite number. So I biased it at 0.7 and you get a current density of 144. Right? So how good is this estimate? Well, you do simulation. So in simulation, for example, if I do, look at the current gain. How do you estimate the unity gain frequency? So what you do is, you take the transistor, as I've discussed again. What you do is, you bias it at, let's say 2 volt forward active. You bias it in the forward mode, let's say here, and then you apply a sinusoidal current, into this, and then you measure the sinusoidal current that comes here. Okay, and you take the ratio. So this is the plot that one gets from the simulator. Current gain beta as a function of frequency, and then we go and I'm looking at this is 0, but one should look at a little, not exactly 0, but a little bit above, at 1 when beta falls to unity gain frequency here. So it's around, as you can see here, FT is 1.5 or 1.7. This is when beta falls to 0, 1.52. Okay, so it will go to something like 1.7 or so gigahertz. And our estimate is 2.2. So it's not bad, if reasonably close for a quick, simple calculation. Right? So this is the delay of how fast is your bipolar transistor. Okay, characterized by unity gain frequency. And this is a number. So this is where you are, correct? Your transistor is working somewhere between 1 to maybe around a little less than 2 gigahertz according to simulation. Right, so now you want to make your transistor fast. You want to make it faster. Right, what should your strategy be? Look at all the delay components are there. You want to make it faster. What would you do? Quickly, if you want to make improve the speed of the transistor, which is a dominant component of delay? Emitter junction capacitance, and collector base is not that there, but both of them, let's say if I look at it, they form 77%. So if I want to make my transistor faster, a very easy way to do it would be, note that, increase collector current density, operate it at higher current. Given a transistor, bias it at higher current. Right now, note that my area of the transistor is 10 per minus 8 centimeters square, 1 micron by 1 micron. So my current that is flowing in my device is 144 multiplied by 10 per minus 8 ampere per centimeter square. So you can see how much is the current. Right, so this is equal to 0.014 something like milliampere, right? I think 0.014 milliamp. So, increase the current density, increase the collector current, bias your transistor at higher current. So if you bias it at higher current, these delays should come down, right? So if I simply increase the current by a factor of 10, this should become 4 picosecond. This should become 1.2 picosecond, right? And then these become small, and then I will be limited by this. So a simple strategy, whoever works with bipolar transistors, if you want higher speed, try to operate the transistor at higher current. And you can see why operating at higher current. For a given area, if you increase the current, you're increasing the current density. And your transistor will become faster, right? So what you would try to do is push the current to higher and higher values. Of course, there's a price that you have to pay. Power dissipation will increase. But let's say you're willing to, right now you just care for the speed, right? So you will do that. But then this is what you end up with. So let me push the speed of the transistor. And this is what happens here. So yes, if you push the speed, if you push the current density, it increases. Eventually, do you see that it should become constant? Go back and see. Do you see it becoming constant? Look at the current components, delay components. Delay number 1, 2, 3, 4, and 5. So if you make the current density higher and higher, what do you expect? The components number 1 and 2 will become negligible, and then you'll be limited by 3, 4, and 5. That's it. And 3, 4, and 5 don't depend on the collector current. So you expect delay to improve or unity gain frequency to improve and become level off. So that's what is happening here. It's trying to become, you can see here, constant here. But then if you push it higher also, it starts to drop. Again, because of high level injection effects. But so there is a point where you can get maximum unity gain frequency, where you can see it's independent of current, which means what? That the first two components is possible to reduce it to small value by operating at higher current. And then you will be limited eventually by what? By these components. So our design, the design that we have done, ultimately what am I limited by? Who is limiting my design? I go to higher current density, then the first two components become negligible. Then what am I left with? Base transit time, emitter transit time, and collector transit time, right? I'm left with these three, right? And the most important thing is here in this is in our design, the most important component is 13 picosecond base transit time. And how do I reduce base transit time? Look at the expression. What do you do to reduce the base transit time? Effective base width you reduce. How will you reduce effective base width? Well, right now I chose 300 nanometer, 0.3 micron. So now you'll say, why choose 300? Make it 0.2 micron or even lower. Then what will happen? Punch through will occur. So the device will not work. So now your strategy would be, if you are seeing that I'm eventually limited by this, that I should reduce WB. But at the same time, to avoid punch through, what should I do? I should increase the base doping. Because if I'm reducing WB, but if I'm increasing the base doping, then what happens is depletion widths are not increasing. I'm reducing the depletion widths. So I'm reducing the base width, but I'm increasing the doping and thereby reducing the depletion width so that they don't merge with each other. So this should be your strategy for making the transistor faster. Reduce WB and increase NA. And so do that, and then okay, so I'll let me stop here and let's discuss some. So we'll come to now. So we now know that the most important delay that we are seeing here is base transit time. This one you can see here, WE square by 2 dp by 1 over beta, 1 picosecond, and all that we can reduce even further by, let's say, shrinking a little bit WE also. So this is not such a this thing here, okay, not such a larger delay, but still these two are 1 and 1. You can see here the two delays are comparable in nature here. All right, so think about for next lecture, how do we have 2 gigahertz transistor. How do we create a 2 gigahertz transistor? What do I have to do to create a 200 gigahertz transistor? So we really want to create a world record in terms of the fastest transistor and make it 200. There are higher, there are even transistors with even higher FT. But let's say we want to do a 200 gigahertz transistor. So how do I design a transistor which would have a 200 gigahertz unity gain frequency? Okay, so that's something. Give it some thought, and then we'll come back to that. Any questions regarding assignments or anything?